All right, today we're talking about Chapter 2, Section 5, the transformations of functions. Now, today's going to be today's going to be kind of a hard day, and I know I've said, I think I might have at least, I know I've said in the past, I ramble sometimes, and you might want to speed up the videos, at least like 1.5 times, right? But the thing is, today's going to be a lot harder. There's concepts in here that I really feel like you need to wrap your head around, rewind if you have to, all that good stuff. But today's going to be a pretty difficult day, I think. Um, Not trying to scare you, but I just want you in the right mindset. All right, so starting off, we're going to talk about what I like to call parent functions. Okay, so parent functions are are functions that the behavior of these parent functions is the same throughout. All right, and so you need to memorize what each algebraic equation corresponds to a parent function. Now, things will change with these parent functions, and that's where the transformation comes in. But you need to know the base form of these equations. All right. So first thing we're going to talk about is a constant function. Okay. The constant function, that's just going to be, the function be f of x equal to some number. Okay. In this particular case, it looks like it's like 1.5. So this is basically saying like f of x equal to 1.5, and then this is what the constant function looks like. It is just a horizontal line. Uh, Now, for every single one of these, see that the domain is, well, I guess besides the square root. For every one of these besides the square root function, the domain is always negative infinity to positive infinity. The range, again, now the range is where we appear on the y-axis. The range is just simply going to be wherever we see our constant function. It's constant from negative infinity to positive infinity, and it is considered an even function, which we talked about in the previous section. The identity function is f of x equal to x, and it's just a slanted line like so. Now we're going to come back to identity function later when we start talking about inverse functions. Well, all of these need to be memorized. That's another thing. Every one of these has to be memorized. So get to it, right? The domain is negative infinity to positive infinity. The range is the same. And of course, we see that we're increasing from negative infinity to positive infinity. And this is considered an odd function because we are symmetric about the origin. The absolute value function, it creates a v. Okay, we have our domain, again, negative infinity to positive infinity. Our range, this only exists from 0 to infinity, including 0. We see that we're decreasing from negative infinity to 0, and we are increasing from 0 to infinity. And this is an even function because we are symmetric about the y-axis. Kind of the same here. This is our quadratic function or the square function, right? The domain is negative infinity to positive infinity. The range is 0 to infinity, including 0. We are decreasing from negative infinity to 0, increasing from 0 to infinity, and this is also considered an even function because it is symmetric about the origin. The square root function looks like this, okay? And again, every single one of these, you need to be able to memorize what the behaviors are because then we're going to put transformations on them. And of course, you'll see that later on in this lecture. But our square root function here starts at 0, 0 and shoots off. Okay. The domain is from 0 to infinity. My range is from 0 to infinity, and we are increasing from 0 to infinity. Okay. And of course, since this has no symmetry, it is neither even nor odd. Now, these two are two functions that I think are kind of confused a little bit. Um, they are the cubic function and the cube root function. Okay, so real fast before we even continue, so hopefully I think the quadratic function should probably be burned into your brain by now, right? It's a parabola. We know all about parabolas, and the square root function behaves like so. All right. Well, the cubic function basically has half of the quadratic function, right? And then it shoots off down here. Whereas the cube root function, all right, it's a root. It behaves kind of like the square root function. It kind of like shoots off to the right as opposed to shooting up like the cubic function. And of course, it's an odd function, so it's symmetric about the origin like so. Anyways, let's talk about the cubic function here. It behaves like so. The domain is negative infinity to positive infinity. The range is negative infinity to positive infinity. It is forever increasing. It is always increasing. Okay, so if it's increased from negative infinity to positive infinity, and it is an odd function. Cube root function, like I said, I mean it behaves kind of like the square root. It's just it shoots off down here, unlike the square root. The domain, range, and its increasing is the exact same as a cubic function, and it's also an odd function because it is symmetric about the origin. Now, I said all that inside 5 minutes, but these need to be memorized. All right. Maybe to make things a little bit more simple, you don't necessarily have to memorize the domain, range, increasing, or odd. Mainly because if you can memorize the behavior of the function, then you can pretty much deduce that on your own. But these 6 functions, you need flashcards, do something. Right? Draw a horizontal line, say identity function on the back. Draw a V, say absolute value function on the back. Draw a U, say standard quadratic function on the back, and so on. These need to be 100% memorized, and there's no way around it. And the reason why is because we're going to be doing our transformations. The first concept we're going to talk about is a vertical shift. So vertical shift is the easiest concept, which is why it comes first. Right? And this is where, let's actually put vertical shift and horizontal shift on the same page just to really drive home the differences. Okay, so vertical shift and horizontal shift, they are how you think they are, right? One is a vertical shift up and down, and one is a horizontal shift left and right. So looking first at vertical shift, right? If we have some function f and c is a positive number, it doesn't matter what the number is, right? Then if we take the function and then we add or subtract that positive number, all right? If we add, we shift vertically upward. If we subtract, we shift vertically downward. Okay? And looking at our drawing here, the black is my original equation, and if we add some constant, we shift up, and if we subtract some constant, we shift down. Right? So a vertical shift, we are adding or subtracting to the parent function. The parent function being one of these, which we'll see here in a moment. All right, we're adding or subtracting to the function. A horizontal shift, okay, while I still have that thought process of we're adding or subtracting to the function of vertical shift, horizontal shift, we're adding or subtracting to the variable. Okay, notice how we are adding some number to the variable and we are subtracting some number from the variable. Unlike over here, the plus c and the minus c are not inside the x. We are not adding or subtracting to the variable for vertical shift. All right. So if we are adding a function, or if we're adding some constant to x, then we shift to the left, and if we subtract, we shift to the right. Now that might not seem very intuitive, right? Because obviously for a vertical shift, we know that, or it makes sense, right? If we add some number, then we go up. If we subtract some number, we go down. Okay. Well, horizontal shift might not, on the surface make intuitive sense, but think about this, right? If we have x plus c, right? X plus c, and then if we equate that to 0, right? If we just basically solve the problem, then we get, we subtract c from both sides, and we end up getting x is equal to a negative c, which is why we shift to the left as opposed to the right. Okay, so it is intuitively it's a little backwards, but if you do the algebra, then it makes complete sense. All right, now that is horizontal and vertical shift. Of course, we'll do an example. We'll look at the examples, but I really want to showcase the difference between adding and subtracting to the function versus adding or subtracting to the variable. Okay, so let's look at a couple vertical shifts first. And honestly, I'm pretty sure, I think I can just go ahead and snip these examples. So let's go and just snip these examples and show you here, as opposed to drawing graphs. I feel like sometimes making things look nice and pretty is better than actually, doing the arithmetic for you. Okay, I think this is perfect. All right, so example one it's asking us to use the graph of the absolute value of x, and of course we know that to be a v. Okay, this is why you have to memorize those seven um, parent functions. Okay, so once you memorize what the absolute value of x looks like, we know it's a v. Okay, well, if we have the absolute value of x minus 4, notice how we are subtracting. We're subtracting from the parent function, and therefore we will make a vertical shift down. Now, the vertical shift happens basically here at 0, 0. So this is what I call a landmark. You're basically taking this point at 0, 0, and by the way, it's 0, 0 for every one of these equations. All right. We will see for exponential and logarithmic, it's going to be a little bit different, but that's going to be later on in the class. Well, not class. The semester. Later on in the semester. So you basically take 0, 0, and then you just go down 4 units. Pop, 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 right there. Right here at 0, 4, we see that we have that V shape, and we moved our landmark down from 0, 0 down to 0, 4. And that's a vertical shift. Okay, so again, keep in mind, vertical shift is if we add or subtract from the parent function. Now looking at the horizontal shift, we are adding or subtracting from the variable. Okay, so this reads, use the graph of f of x equal to square root of x. Well, again, you need to be able to memorize what the square root of x looks like. And the square root of x starts at 0, 0, and it shoots off, like so. Okay, and so if we start at 0 and shoot off, again, 0, 0 is going to be my landmark. Okay, well, looking at this, it is x plus 5, right? And of course, our rule, if we add to the variable, we shift left. If we subtract from the variable, we shift right. Well, it looks like we are adding to the variable, so we're going to shift left 5 units. We're going to take this landmark right here at 0, 0, and we're going to shift left 5 units. So we're going to shift left 5 units, and then my new absolute value, not absolute value, my new square root looks like so. Okay. Now again, I'll even admit, I mean, it feels kind of lazy, just kind of, using the laser pointer on these graphs. But I mean, you've seen that I do the arithmetic when I can, but in this particular case, I really feel like it's better to make this, presentation nice and neat as opposed to drawing these graphs myself. All right, so this example is a mixture of horizontal and vertical shifts. And let me see. Okay, we don't actually talk about it just yet. Okay, well, I'm not sure why we would introduce this first as opposed to telling you, because there is a particular order that you need to do your transformations, right? And that order is horizontal is always first. You always do the horizontal shift first, and you always do the vertical shift last. 100% of the time, that's the rule. Okay. Now, for a problem like this, I don't think it really matters, but we're gonna have to start talking about reflections, well, I'm not sure shrinking and squeezing really matters, but definitely with reflections, then it's really gonna matter. So remember, horizontal shift is always first. So looking at this particular problem, we see a +1, so we know we're going to shift this to the left 1 unit. And of course, that's what we see here, right? Well, first of all, hey, I guess I can go ahead and draw this one first, right? We know that my parent function looks something like this, okay? Now, obviously, we didn't have the parent function given to us, but we know that's a parent function because that is the graph of f of x equal to x squared, okay? So this is my parent function, and the first thing we're going to do is we're going to make a horizontal shift left 1 unit, and we see that with this graph right here. And then lastly, we're going to do a vertical shift down 3 units. And of course, this is our final graph. Now, I can't remember if I actually said this or not, but in a previous, I mean, I can't remember if I said it, but in your previous courses, right? If we were to look at this function right here, and you were asked to plot that on the graph, okay? Well, what would you do? Well, you would more than likely make an x y table, right? And then you start like -3, and then -3 plus 1 is a -2. -2 squared is 4. 4 minus 1 minus 3 is a 1. And then you'd say here at -3 you have a negative. No, you have positive 1. Sorry, you have positive 1, and then you would connect the dots. Okay. Well, thing is, now we're into college algebra. Now we're into things that are a little bit harder. And so now you are going to be tasked with looking at this function, the one I have circled right here, and being able to graph it without doing this table over here, right? Everybody can do a table. You start doing these tables when you're in 5th grade. Everybody can do that, right? But now we're going to be taking this function and saying, okay, so I am adding 1 to the variable, so it's a shift to the left 1 unit, and I am subtracting 3 from the parent function, so that's going to be shift down 3 units. Okay. Next up, we're going to talk about reflections. Okay, so similar to what I did with the vertical and horizontal shifts, I'm going to go ahead and put the reflections on the same page so we can operate that way. Again, just to show the differences between a reflection about the x-axis and a reflection about the y-axis. So let's put this over here, put that right there. This example. Oh, that's not all of it. Let's try that again. Okay. So again, showing the differences of reflection about the x-axis and reflection about the y-axis. Okay. So starting, and we're just going to look at these two definitions first before we look at the examples. So starting with reflection of the x-axis, we know that if we see that we have, if the graph of y is equal to negative f of x is the graph of y is equal to f of x reflected about the x-axis. Okay, so similar to the vertical shift, right? Remember, vertical shift, we added or subtracted to the parent function. For this, if it is a negative of the parent function, we reflect about the x-axis. Over here, if the graph of y is equal to f of negative x, that's the negative of the variable. Okay, so notice the difference between y is equal to f of negative x, which is a negative of the variable, and y is equal to negative f of x, which is a negative of the function. Okay, notice how the difference is there. So if we have the negative of the parent function, we're reflected about the x-axis. If we have the negative of the variable, we reflect about the y-axis. And again, guys, please take your time with this section. This section is one of the harder sections that we're going to do in this class. If you need to rewind this, watch this, email me, do whatever you need to, because if you don't understand this, it's going to be very hard to proceed in this class. All right, but anyways, let's look at example 4. It says use a graph of f of x equal to cube root of x. Well, again, we have to remember what the cube root of x looks like. And again, it looks like that s. Okay, that's the parent function. And we're wanting to obtain the graph of negative cube root of x. So this is the negative of the parent function, right? Notice how the negative is not in front of the x, the negative of the parent function. So we're going to reflect this about the x-axis. Now, this is an odd function, so it's also reflected. It looks like it's reflected about the y-axis as well. But we're reflecting this about the x-axis, and basically we just take this function and we just kind of rotate it. We rotate it about the x-axis. All right. The next one, notice how we're looking at the negative of the variable. Okay, so we're going to use the graph of f of x equal to the square root of x to obtain the graph h of x, which is the negative of the variable. So this is the square root of x. We know that the square root looks something like this. Well, this is the negative of the variable, so we're going to reflect it across the y-axis, like we're told here. Okay, so that's reflection about the x-axis and reflection about the y-axis. Now, real quickly, when we had this particular problem, when we combined horizontal and vertical shifts, I said horizontal shifts are always first, vertical shifts are always last. Okay, well, what happens with our reflections? Well, we'll talk about that here in a moment. All right. Now, next we're going to talk about vertical stretching and shrinking. Now, this is especially if I were to freehand this. This is, I wouldn't say more or less subjective, but it's a lot harder to do freehand. So let's put this over here, and similar to how we've been doing for this entire section, let's go ahead and put the horizontal shift next to the vertical, the horizontal stretching and shrinking next to the vertical stretching and shrinking to really show you the difference between the two. Okay. Now this definition is a little bit longer, as you can tell, but it's, well, no, I'm not going to say that. But okay, so vertical stretching and shrinking, okay? If we're going to let C be greater than 1, all right, so we're basically looking at a whole number versus a number that's between 0 and 1, okay? Notice how we don't talk about anything about C being less than 1, right? Not saying C is less than 1. That's because we've already kind of taken care of that with the reflection about the x-axis, right? Because if my constant, right, if my constant is a negative number, well then it's going to be, one of these two, reflections about the x, reflection about the y. In this particular case, we're just going to look at is the constant in front of my function, is it greater than 1 or is it between 0 and 1? Okay, and that works both ways for vertical stretching and shrinking and horizontal stretching and shrinking. Okay, if my constant is greater than 1, all right, so if I'm multiplying my parent function by a number that's greater than 1, it could be 1.2, it could be 1.1, does not matter. If it is greater than 1, then we're going to vertically stretch. Okay, now it's a little bit, obviously I'm just going to have to maybe try to describe my hand movement here, okay? Maybe not, oh, let's see, how would I describe this? Okay, so no. Okay, yeah, we'll do that. Okay, so vertical stretching. If I were to have one hand on top of the other, okay? So one hand, let's try this. All right, so this is this is one hand, and this is the other hand. Okay, these are my hands. Let's give me some Disney mitts here. Okay, so here's my Disney mitts. Okay, so one hand is over the other. Okay, if I were to pull pull one hand up and shoot one hand down, notice how I'm vertically stretching, right? Basically pulling them apart, I'm vertically stretching. I don't know if that concept really is driven home here, but the idea here is this: we're stretching. Okay, so this blue line is my parent function, and this red line is I am multiplying my parent function by some value c greater than 1. So I'm stretching my graph. Okay, well if I were to take my mitts here, and if I were to push them towards each other, notice how I'm vertically shrinking. And of course, that's what we see here. Okay, the blue line, f of x, that's my parent function, and then I'm essentially smushing it down, right? If my number is between 0 and 1, I'm smushing it down. So I'm vertically shrinking. Okay, now obviously on the other side of that, we have our horizontal stretching and shrinking. So and I just realized that my Disney mitts should be white, huh? So here are my mitts. Okay, and we're going to talk about horizontal stretching and shrinking now. So, kind of the same concepts here. We're going to deal with number that's greater than 1 and number between 0 and 1. Okay, if we are multiplying my my variable. Sorry, if I'm multiplying my variable by a number that's greater than 1, then I'm going to shrink. I'm going to shrink the graph. And again, you can see that here. The blue line is my parent function, and then I'm just going to shrink it. I'm pushing it together. And then of course, the other side, if I have a number that is between 0 and 1, we're going to have a horizontal stretch. Okay, so really quickly, on every concept we've covered so far, remember or notice how the one of them is always the opposite of the other, right? Well, same thing here. So if for vertical stretching and shrinking, if we have a number greater than 1, we are vertically stretched. For horizontal, if it's greater than 1, we're horizontally shrunk. the exact opposite. And then same thing here. We're going to shrink it vertically between 0 and 1. Whereas if we were talking about horizontal, we're going to stretch it. Okay, so they're the exact opposites. So let's look at some examples. I don't know if they'll fit on this page. If not, maybe I'll shrink it down a little bit, both horizontally and vertically. Huh? Okay, so yeah, this will fit. Okay, good. So let's go back to the horizontal stretching and shrinking. Oh yeah, I think it'll fit. So again, let's snip this and put it underneath the horizontal. I'm sorry, the vertical. Ugh. Saying those two over and over really does get kind of tiresome, but it is what it is. Okay, so here are my examples of vertical stretching and shrinking. So looking at vertical, we're going to take the function x cubed. Okay, so again, we know the x cubed looks something like this. So, and we're multiplying it by 1/2. Well, 1/2 is a number between 0 and 1. So if it is a number between 0 and 1, we're going to vertically shrink it. All right, so we're going to do that compression, right? So we're going to take my two hands. Well, I guess it'd be on this one. We're going to take my two hands. Here's one hand, here's the other, and we're going to push it in. Okay, and I guess it's kind of hard to see here, but this is the graph that is a vertical shrinking. Okay, if we were to have vertically stretched, right? If this was not a 1/2, but instead it was a 2, well then my graph would look something more like this because I'm vertically stretching it, right? I'm pulling it. Okay, and again, notice the difference between multiplying by the parent function and multiplying by the variable. Okay, 1/2. Um, so notice those two differences. Over here, looks like we have two different ones. Looks like we're going to be in a horizontal stretch and a horizontal shrink. So starting with 2 times x, right? 2 is going to be, okay, never mind. I guess, all right, so b is going to be on a different page. Oh, there it is, yeah. B is on a different page. Maybe I can fit that in. Or maybe, honestly, we can kind of freehand. It's not a big deal. So if we have our function now this is, we're not using a parent function for this one, right? This is just some function. Doesn't matter what the function is, but we're multiplying by 2x, and this is the function, just something completely random off the wall. Well, if I'm multiplying it by a 2, that's a number that's greater than 1, right? So it's going to be the exact opposite. So if it was greater than 1 vertically, we would stretch it, but since it's horizontally, we're going to shrink it because we're multiplying by the variable. It's 2 times x. Over here is 1/2 times x. And again, you might not understand this concept. I don't know, but and sometimes I ramble and try to over-explain things, but this is really important. Notice how we're multiplying by the parent function, which is x cubed. Okay, so those are the differences. But anyways, notice how for a, it's 2x, and so we're going to horizontally shrink it. And so we're taking this graph, and we're just basically playing an accordion, right? And we're pinching it in to itself, and we end up with a pinched in graph. Well, the opposite of that would be this particular problem here. It is h of x equal to f of 1/2 x. So I'm multiplying by a number between 0 and 1. So I would stretch this, right? So I would stretch this out, and it would look something similar to that. And let's actually go ahead and snip that so I can get you a better idea of it. This would be B. I'm not sure if it'll fit. Yeah, it's not the greatest fit, but it's there. See, so notice how we stretch. Okay, so that's vertical stretching, shrinking, and horizontal stretching and shrinking. Alrighty, so the sequence. I said earlier that horizontal is always first and vertical is always last. Well, this is the order you have to do it in. Okay, now I want, well, I hesitate to say this because I don't want to steer you wrong. But I'm pretty sure as long as you do horizontal shift first and vertical shift last, you'll be okay. Okay, but if not, uh, there's a mnemonic device. Well, there isn't a mnemonic device, but this was, you know what? Here we go. Story time. So if you read my bio at the end of the syllabus, I told you that you know what? I just was not a good college student at first, right? I didn't treat it uh, seriously. I got kicked out a couple times. I'm in tremendous student loan debt. Um, and well, at some point, I decided to turn it around, and here I am now. I've finished my master's. I'm teaching this now, and one of the things I did was I was like, you know what? I'm not as smart as I think I am. I need to figure out how to study. And one of the main things that helped me through a lot of my classes was mnemonic devices. And a mnemonic device is basically you just make up a sentence. Okay. So looking here, we have steps 1 through 4. And so starting here, it looks like horizontal. That's 1. 2 is stretching or shrinking, which they're both S. That's perfect. 3 is reflecting, and 4 is vertical. Now, make a mnemonic device here. Um, uh, I don't know. He sits right van. I don't know. I this is just basically it's open to interpretation. Whatever you want. If you just want to memorize HSRV, then that's just fine. But it's not that hard. You memorize this. But like I said, I'm pretty sure if you just do horizontal first and vertical last, at least in this class, you'll be a-okay. Okay. So let's go ahead and erase this and put the example that probably does all of these up. Yes, example 8. Okay, so for this, you know what? Let's just do this. We can put all that on there. I wonder if this will fit. It's gonna be close. Oh no, it's not gonna be close. That's easy. Okay. Yeah. Okay. Alrighty. So looking at this example. All right. So these equations that look like this. Okay. It says y is equal to negative 1/2 times f of x minus 1 plus 3. Okay, now these equations are set up to just be some off the wall equation, which is this. All right, doesn't matter what it is, doesn't matter what it looks like, but for these examples, it's not really giving us a parent function. Again, those parent functions were those 7 functions earlier. It's not necessarily giving us a parent function, but it's just some function. Okay, so we have some function, and we have to perform these transformations. Well, horizontal shift is first, then we stretch or shrink, then we reflect, then we vertical shift. Okay, so let's start with the horizontal shift. Looking at this particular equation, we see that we are subtracting 1 from the parent function. Okay, so if we subtract 1 from the parent function, then we know that we are going to move to the right 1 unit. Okay, and of course that's what we see here. So this is my parent function for this particular function, right? It's not one of the parent functions we went over, but this is my original function. And we're going to do the first transformation. We're going to add 1, and so we're going to take the landmark at 0, 0, and we're going to move it to the right to 0, 1, or I'm sorry, 1, 0. And that's what we did here. We basically just moved everything to the right. Okay, so that's my horizontal shift. Second is a stretching or shrinking. Looking at this particular function, we are multiplying the function by a negative 1/2. Okay, now we're just looking strictly at the number. Now this is where I feel like what I was trying to do was I was trying to explain earlier. Um, with my constants here, notice how we don't even talk about negatives. That's because the negative is will be in regard to the reflection about the axis. Okay. For this, we're just looking at the number, and we're just going to ask ourselves: is this number greater than 1? No, it's 1/2. Right. So it's between 0 and 1. So we know that we're going to have a vertical shrink. Okay. We're going to shrink it by a factor of 1/2. Okay. Now again, this is more or less up for interpretation, because I mean I'm sure, I mean I don't have the idea of a factor of 1/2, right? But we're going to shrink it by a factor of 1/2. So we're going to take our function here and we're just going to flatten it. Our hands are on top of one another and we're just going to flatten it. And that's what we see here. We just basically flattened it, right? The parabola looking thing here is a lot flatter. My triangle is a lot flatter. We just flattened it a little bit, okay? That little bit is a factor of 1/2. Next up, we're going to do the reflecting, okay? Well, do we have a negative of the function or a negative variable? Well, x is just simply x, right? So since it's just simply x, we have the negative in front of the function. All right, well, the negative of a function, we reflect about the x-axis. So we'll take this function, and we're going to rotate it about the x-axis. So this parabola is going to be down here, and this, triangle still kind of, it'll be up here. And of course, we see that right here. We have that parabola down here and the triangle up there. And then lastly, we have a vertical shift up 3 units. Okay, so you just basically pick some landmark and move it up 3 units. And of course, -3, 0, all these points here, you'll notice that they will be shifted up 3 units. And my final graph looks like this. Okay, now today's lecture was a lot of hand waving. Okay, and I'm really sorry, but I don't want to draw the graph and just make it ugly. But we're at 36 minutes right now. If you need to watch this lecture 2, maybe 3 times, okay, 100 minutes, right? Please do it. This is probably the hardest concept that we're going to go over in this class, and I mean that, okay? Unlike previous lectures where I was like, hey, you've seen this before, you might not have seen this before. This is a little bit more difficult, but you must know how to do this before we proceed. So, realistically, guys, spend 100 minutes, all right? Watch this 3 times, and fully understand, fully grasp these concepts, please. All right? Well, with that said, that does conclude today's lecture.